So why we need the half-life period means that all the atoms takes to disintegrate completely. It takes time for up to infinity. So we have to differentiate the element. That's why we need the half-life period. The half-life period means half of the element is completely disintegrated. That means 100% element is there. That what is the time taken to the element to decrease up to 50%? That's called half-life period. The half-life period, some elements is takes 10 to the power of 14 years, some elements is takes 10 to the power of 14 seconds. So using that we can classify the element. So here T equal to T half. So time period we can take it as T half. N equal to N0 by 2. N0 is the total number of atoms divided by 2. So substituting that value in this equation. So N equal to N0 by 2. That value is substituted here. So instead of N we are writing N0 by 2. So T equal to, we can write T half here. So N0 cancel each other. 1 by 2 is here. So taking reciprocal. So you will get 2 and this negative sign becomes positive sign. So taking that exponential ln on both sides. So when you take the ln on both sides, exponential cancel. Then ln 2 is here. Ln 2, then lambda T is there. So lambda is brought it here on the side. So ln 2 value is equal to 0.6931 divided by lambda. The same time you can write that 50%, 25% the disintegration rate. So how many times it takes that to disintegrate? For example, you can take 1 time or 2 time or 3 time, whatever it is. That we can write n equal to 1 by 2 whole to the power of n into n0. For n equal to small value, n equal to 1, you put 1. So 1 by 2 n0, that is n0 by 2, you will get 50%. Suppose 2 times it is decayed. So you have to write n equal to 2. So 1 by 4, that means 25%. Suppose put n equal to 3. So here 9 will come. So that is 12.5%. Like that you can calculate. The same thing, decay constant and radioactivities are equal. So you can see that the same thing is also, you can use R is equal to 1 by 2 whole to the power of n R0. Next one is mean life. Mean life is defined as a, mean life is defined as a, so all the atoms takes to lifetime of infinity. So to classify that atom, so meaningful average the value of lifetime is called the mean life. So the mean lifetime of the nucleus is the ratio of sum of integration of lifetimes of all the nuclei. So we have to sum all the lifetime of all the nuclei divided by or all the nuclei to the total number of nucleus present initially. So we have to add the lifetime of all the nucleus to the number of nuclei present in the initially. So substituting that value, you will get this equation. So on simplifying this equation, you will get this equation. So these two equations is enough for us because the simplification is given here, but that is not for exam. So if you need, you can use it. Okay. So see the relation, that is very important. Tau equal to 1 by lambda. Tau equal to 1 by lambda. So tau equal to 1 by lambda. The tau equal to 1 by lambda is substituted in the equation in here. See, T half equal to ln 2 by lambda. So 1 by lambda is here. Substituting that 1 by lambda, you can write T half equal to tau into ln 2. Tau into ln 2. So ln 2, you know that 0.6931 into tau. So this is the relation between the half-life period and mean life period. So carbon dating, I already told you that. So from sunlight or the cosmic ray, the carbon 14 is present in the atmosphere. So that can be absorbed by the all the living things and non-living things. So it's a carbon 14. Nitrogen reacted with the sunlight, it produces the carbon 14. So all the living things taking get the carbon 12 or the carbon 14. So everything in nature, the ratio of the carbon 14 and carbon 12 kept constant in the nature. Suppose that living things is died, that carbon 14 starts to decay. So carbon 14 starts to decay means It is a radiocarbon dating. It takes half-life period by taking 5,730 years to decay. So using that, we can calculate the age of the system. For carbon 14, there is a nitrogen 14, electron plus hydrogen. So using that, we can calculate the radiocarbon dating. So this is the law of disintegration. How to derive the law of disintegration? N be the total number of repair. Sample, you are going to take delta N, the time period of delta T. So this is the equation. Probably we computer, the lambda of radioactivity constant. So the short interval of time can take as dt 12 interval. So integrating on both sides. Next thing is discovery of neutron. So neutron is discovered by Chadwick, the James Chadwick in the year of 1932. But before that, 1930, German physicist Bode and Better conducted experiment. Yeah, beryllium is bombarded with the particle, the alpha particle. So high penetrating radius was emitted. So some invisible rays is highly penetrating radiation is emitted. Initially, they thought that there is a gamma radiation. But 1932, Chadwick discovered that it is not electromagnetic radiation. It is a greater mass, and it is a neutron. It is not affected by the electrical magnetic field, but it has a greater mass compared to the proton. That was discovered by the Chadwick. So beryllium is bombarded with the alpha particle with the carbon 12 plus 1 neutron. Then neutron is stable inside the nucleus, but outside it is not stable. Okay. So its lifetime is only 13 years after it will get disintegrated. So it has the three types of neutrons are there. One is the fast neutron, slow neutron, and thermal neutron. It is classified depending on the energy. Slow neutron means it's 0 to 100 electron volt. Okay, so 100 to electron volt, and fast neutron is 0.5 mega electron volt to 10 mega electron. Thermal electron is very small, 0.025 electron volt. The thermal neutrons and the slow neutron are called slow neutron. These neutrons are used in the nuclear reactors. Okay. So next thing we are going to see that nuclear fission reaction. So nuclear fission. So it's a very important reaction. Already you know that you studied in the 10th lesson. So 1939, German physicist Otto Hahn and Staffman discovered the nuclear fission reaction. Nuclear fission is already we explained that the process of breaking up heavier nucleus into two lighter nuclei releases a large amount of energy is called the nuclear fission reactions. Nuclear fission reactions, it has the different types of reaction. Nearly it has the 90 types. So 90 types, in that 90 types, usually they are studying only these two types. That is uranium 235 92. It is bombarded with the neutron. It is uranium 236 and 92. It gives the barium and the krypton and plus 3 neutrons plus energy. This is one form of equation. Another form of equation, again uranium 235 and bombarded with the neutron. It goes to excited state. The star indicates the excited state. That is unstable state. That uranium is unstable state, and it produces xenon and strontium plus 2 neutrons releases plus large amount of. So it releases 3 neutrons, and this equation releases 2 neutrons. Averagely, we can take 2.5 neutrons are releases in nuclear science reaction. That's the thing we are going to take. In that nuclear reaction, so uranium 235 is here. So neutron is bombarded with the uranium 235. It is split into two elements, krypton and barium or strontium or xenon, and releases the 3 neutrons. That 3 neutrons, again, it's interacted with the uranium 235. Again, the 3 becomes 9, 9 becomes 27. Like that, it will progress. So when it goes up to 100 steps, it goes to 100 steps. What will happen? That energy of the electron. So it goes to 100 steps. It releases a very large amount of energy. It's called the uncontrolled chain reaction. Now you can see that energy released per fission. So see that uranium-235 gives very many krypton plus 3 neutron. So here mass of the uranium, neutron and the reactant. So this is the total mass of the reactant. So see, the total mass of the product is that 14091 and you are adding that you will get this value. So it is not equal to the reactant. So what is the difference in that mass? That is equal to delta M equal to, so 0.225303 is the mass difference. That is mass difference. Add that mass difference into that 931 mega electron volt, you will get 200 mega electron volt. So the mass of the mass change in that mass or mass defect or delta M is converted into the energy of 200 mega electron volt. So that energy is used as the kinetic energy of the daughter nuclei, and later it is transferred to different form of that energy. It may be a light energy, heat energy, or pressure energy, or sound energy, like that it will change. Chain reaction. Chain reaction, only I explained that. Then the chain reaction takes place when uranium is combined with the neutron. It gives the 3 neutron. Again, the 3 neutron is combined with the uranium. It will give 9, 27. It will go up to geometrical progression. So we can't able to connect it, calculate it. It will go geometrical progression. Then the two kind of chain reactions are there. One is the controlled chain reaction. Another one is the uncontrolled chain reaction. So the controlled chain reaction is it occurs in the only nuclear reactor. But uncontrolled chain reaction, this example is atom bomb. So atom bomb, you know that is nuclear fission reaction is taking place in uncontrolled manner. So it releases very large amount of energy. So it produces a massive destruction. So you know that in World War II, the 1946 August 6 and 9, USA dropped the 2 atom bombs in 2 places, Hiroshima and Nagasaki. You know that as a result of lakhs of people killed and 2 cities were completely destroyed. So even now people who are not living in that place because it creates problem and it gives the side effects to the people. So next thing is, so when that progression, I told you now that 3 neutrons are 3 neutron, again it is converted into 9, then 27, it will go like that. Then finally it reaches that, suppose in 100th step, it will go to 2.5 into 10 to the power of 40. So multiply 200 mega electron volt, you can get 8 into 10 to the power of 29 joules. So it is a very large amount of energy. So using that energy, you can use the electricity for Tamil Nadu in several years. So total Tamil Nadu can use the energy for several years. So very high, very large amount of energy. See the next thing, suppose you are using the 100 watts bulb. That 100 watts bulb can glow up to 30,000 years. Or if you need the same energy from TNT, you need that 20,000 tons of TNT. You need to blow the 1000 watts bulb up to 30,000 years. So you can compare the two values, 20,000 tons, and the atom is only 100 step occurs. It produces the same energy.